Fijalkow, who will be talking about simulations and bisimulations for probabilistic systems and their logical content.
Thank you. Well, of course, I changed the title, but it's about the same.
Simulation has disappeared.
Simulation has disappeared, but I'll mention it anyway. Okay, so thanks for coming. So now I'm a research fellow at Simons. I'm glad and grateful to be a research fellow at Simons. And I want to talk about ongoing work about bisimulation for stochastic systems. So let's start. What is the model? So the first one we're looking at is very simple Markov chains. So we have states, and for any state we're giving a distribution. So here D of Q means sub-distribution. I actually almost never care for distributions. They don't have to sum up to 1. So here from this state we have the distribution 1/3 and 1/2. So what we're interested in this is, let's say we start from the state on the left, and if we do one step, then we will be in this distribution 1/3 here and 1/2 here, and then I compute the sum of those two numbers. So I'm really interested in the probability to still be in the Markov chain after some steps. Right? Here, there's 1/3 here, 1/2 here, and you can think that there's somewhere some bottom state, some sink state, that is reached with priority 1 minus those two guys. Okay? So at every point, we're really interested in the probability of remaining in the Markov chain. So if I do just one more step, then I will be here with priority 4/9, and here something, and the sum of those two is this. So you can take your Markov chain, and you can have labels. So here I should say that it's not exactly the same terminology as, for instance, Prakash would use. So I believe Prakash would call this a Markov process. I just want to make a difference because then I'll talk about something related. So now I have a finite set of labels, or finite, or doesn't have to be finite. So here A and B. If from this state we have A, then there's one distribution attached to it. And if there's a B, then it's a different distribution. So those labeled Markov chains, I will see them as inducing this function. Let's say it's the semantics of this Markov chain or something. So when you read a word, a finite word, then you're looking at the probability, you're simulating it, and you're looking at the probability to still be there. Right? So let's say for A, then this would be 1/3 plus 1/3. And then I would continue. Okay, so those are labeled Markov chains, and when I will want to say something about them, I'll talk about the functions they induce. And now the third model is the one where you actually add some control, so which is labeled Markov decision process. And here the control is not the actions, so I still have some actions, but this is not what you're controlling. What you're controlling is which distribution are you taking. So let's say we're here and the letter A appears, then you have a choice between this transition and this transition. So this distribution here, 1/3, 1/3, or this one, which is just 1/4. Okay? Actually, it doesn't really matter for this talk, but you allow convex combination of those. So if you have the choice between this and this, you actually have the choice between all convex combinations of those two distributions. It's important, and I think it makes sense for modelization, but it doesn't matter for this talk. So that means that here we really have some control, so we'll talk about strategies which really tell you when you're simulating it, this decision process, when you have a state and a letter, which transition you choose. Okay, so it will be a function like this. So when you fix as a strategy an MDP, then it induces a Markov chain. Yes, Anupam?
Sorry, what's a convex combination?
I mean, it just says you can do, for instance, half of this distribution plus half of this one.
Isn't it the same as d of q?
It is, yeah, it's exactly the same. Yeah, I could have written d of q, but it would give you the impression that it's random. It's just a choice of, yeah, mathematically it's d of q. So does it make sense?
Yeah.
So yeah, you could do like half of this one plus half of this one, if you want, or 1/3, 2/3, or even 1/3, 1/3. Good. So now, well, we want to reason about stochastic models. There are many questions you can ask. Let's start with a simple one. I give you two labeled Markov chains. So they induce these two functions. And I'm asking, are those two functions equal? Exactly equal. So I'm not sure exactly who should be credited for this result being decidable. I like to think of this as a corollary of minimization for weighted automata by Schützenberger, but there are different approaches for this. So let's go a bit more complicated. Last year with Stefan Kiefer and Masha Shirmohamadi in Oxford, we were thinking about this problem that we called the trace refinement. So I give you on one side an MDP, and on the other side a Markov chain. And I'm
sorry, what's MDP?
MDP, Markov decision process. So the last one, the one where you have choice for the distributions. Yeah, sorry, I forgot to mention that I'll use mostly acronyms, and sometimes I recall what it actually means. So I give you an MDP, meaning that I have to give you a strategy. And I'm giving you a Markov chain, so it doesn't come with any strategy. And I'm asking, can I find a strategy for the first one that make them equivalent? Meaning that if I fix this strategy, then those two Markov chains now are equivalent. It generalizes this question. And well, we proved that this problem is decidable in CoNP. And surprisingly, you can ask almost the same question, but saying not for some strategy, but for all strategies. So I give you an MDP M1 and a Markov chain M2, and I'm asking, is it true that no matter what strategies I take for the MDP, it will be equivalent to this Markov chain? And this turns out to be undecidable. Yes?
The second one which you say is in CoNP. Is it also in NP? I mean, it seems to be just existentially quantifying over the...
Well, it's not. The strategy can be infinite memory. So we don't know if it's in NP. We don't know if it's in P. CoNP is the best we have. And I'll talk about this, of course. This is so far what we know. Okay. Yep.
Can you explain the third question again?
Yeah.
You're giving the MDP and the strategy.
No, I'm giving you an MDP and a Markov chain.
Yes.
And I'm asking you, is it true that no matter what the strategy you choose is for the MDP?
You can find the strategy for that.
No, the Markov chain is fixed. So all strategies will give you the same, an equivalent Markov chain, which is equivalent to the one you're given.
Okay.
So it seems to be very strong. There are not so many MDPs that are completely oblivious to the strategy. But this problem is actually undecidable. It's because you can have very complicated strategies that induce very complicated sort of behavior. And it's hard to detect that all of them are equivalent.
So for many MDPs, it must be no.
Yeah. For in many cases, the answer is simply no. And in some corner cases, it happens to be very complicated, and this is what we sort of use to prove undecidability. So why am I talking about this? Because those two decidability results, we actually obtain them by looking at the right notion of bisimulation. So there's this notion that, to the best of my knowledge, was introduced by Hermans, I hope there are no Czech people here, Choll and Kretinsky.
Excellent.
That defines bisimulation not directly as we are used to on states, but on distributions on states. So just take your Markov decision process, this MDP, on which you're deciding for the next distribution, and look at the induced infinite Markov chain, where, transition system where you are really, the states are the distributions of your previous MDP. And now you define the usual bisimulation for it. So you say that two distributions are equivalent if for any letter A, if you can do something on one side, then you can map it on the other side, and it remain equivalent. This is there. And the other way around, if I have delta and delta prime, they're equivalent, I can do something on delta prime, then I can do something equivalent on delta, such that what I obtain, tau and tau prime are equivalent. So this is just the standard definition of bisimulation, but taking it over distributions. What we proved, so first of all, let me start with a folklore result, that if you take two Markov chains, so where you don't have strategies, then being bisimilar on distributions, as I explained just before, is just the same as the equivalence, saying that the two functions for these Markov chains are equivalent. And now, if you're looking at MDPs, if on one side you have an MDP and on the other side you have a Markov chain, then bisimilarity on distribution is really the same as the question I was asking before, meaning does there exist a strategy for the first one that makes it equivalent to the second? So this means that to look at this problem, you can just look more generally at bisimilarity on distributions, and this is what we proved to be in CoNP. So this is the first part of my talk. We were working on this with Stefan Kiefer and Masashir Mohammadi, and we found this notion interesting, the fact that we can relate very verification type kind of question to this bisimilarity and then work on bisimilarity, which has some nice properties. And then I arrived here at Simons, and I started talking to Prakash Panangadan and Bartek Klin, and I realized that I know just nothing about probabilistic bisimulation. And there's a whole world, much bigger. This is what I was telling you about. But there's a whole sets of planets that are all very interesting. And I want to tell you about, let's say, the biggest one, or at least a very interesting one, which is the one you find if you ask Wikipedia or Prakash. It's the same answer. What is probabilistic bisimulation? The notion has been defined by Larsen and Skow in 91. And it's defined for Markov chains, not for Markov decision processes. So you don't have any choice. There's just these labels. The definition is the following. It's an equivalence relation for states. We say that P and Q are two states that are equivalent if for any action A, you're looking at some equivalence class of your bisimulation. Right? So a subset of the states. And it has to be the case that the probability from P reading A to go to C is the same as from Q. And so I'll get back to this definition, but let me first remark that this is actually really different for some deep fundamental reasons from the previous one, from what I was telling you about distributions. Let's look at this very simple example. We have P and Q. And I'm saying that they are equivalent in the very first definition, meaning that the functions are the same. Because what is the function here? Well, in one step, you do 2/3 plus 1/3. So in one step, you're with probability 1 here. And here, probability 1, 1/2 plus 1/2. In two steps, you have 2/3 plus 1/2. This is gone. 2/3 times 1/2. And here in two steps, you have 1/2 times 2/3. So as functions, they really, you cannot make the difference. But now, according to the bisimulation that I just defined before, those two states are not the same. And the reason is that, well, those two are really the same. You cannot do anything from them. And those are also the same because there's just no transition. But this one and this one are different because from here you have 1/2 to go there, and from here you have 2/3. And that directly implies that P and Q are not bisimilar according to the Larsen and Skow definition. So they sort of capture really some different properties that you want to have about the system. It really took me some time to understand this definition, and in particular what's the role of this equivalence class and so on. So the first thing that we did here with Bartek, Lin, and Prakash was to get back to a very usual definition of spoiler and duplicator. When I think about bisimulation, I like to think I have some sort of game where duplicator will try to prove that the two states are bisimilar, and spoiler will try to prove him otherwise, and basically spoiler will try to make some move, and duplicator will have to match it, and they will take it from there. So here's an equivalent game, and if you don't like this definition, then those are like completely equivalent. So you can think about the game. That's actually how I do it now. Although this is really, there's nothing really deep in the equivalence. So the game is the following. Duplicator claims that P and Q are equivalent. Spoiler will try to prove that this is not true. So he will pick an action and a subset C, any subset. And he will say, look, they cannot be equivalent, P and Q, because from P and from Q, the priority to be in C, to go to C, is different. And, well, this is a fact. You're not discussing facts. So this cannot be discarded. This is true. However, a duplicator can say, well, you cheated here, because the C you gave me, it's not an equivalence class for this. So there are some states there that are equivalent to some states outside of C. So duplicator picks a state inside, a state outside, and he says, well, here's how you cheated. You told me that those two are equivalent, and they're not.
Other way around.
And they are. Sorry. Thank you. So this sort of, this shows dynamics on how to prove or disprove that two states are bisimilar for this definition. And you can think about one or the other. So now I have just not so long to tell you about 25 years of interesting research on probabilistic bisimulation. So I'll just mention a few highlights. Well, the first one, I guess for all of this to make sense and to back it up, we can compute this probabilistic bisimulation in p-time. It's actually p-time complete. And I would say a second very strong point is that this has a logical characterization. So you can define a very simple logic such that if two states are bisimilar, then they satisfy exactly the same formula. Conversely, that means that if two states are not bisimilar, then you can find a formula that distinguishes those two. And I see this as a very strong point that this probabilistic bisimulation has really nice properties. And then there are extensions, I would say, in a lot of different directions. You can, instead of talking about whether two states are bisimilar, you can talk about how bisimilar they are. So you can define distances to tell you how bisimilar two states are. You can also have, instead of equivalence, you can talk about some order on this. So saying that a state simulates another instead of them being both ways similar. That comes with nice approximation techniques, and also you can extend this to crazy systems that have infinite set of states, infinite sets of labels, continuous time dynamics, and so on. So this is a very robust notion that has a lot of very nice properties. Now the question that I come up with is, well, all of this is very nice. We know a lot of nice properties. What is this definition good for? So what can we say about this? Do we have also logical characterizations? What kind of things can we do with this? Where does it fit in this big picture? So let me just remind you what are the two notions that exist in this small planet. There is this trace refinement question, which is when I give you two MDP, is the following true? There exists a strategy for the first one, such that all strategies of the second one, this gives me Markov chains, those two Markov chains are equal. And to define a nice relation, a nice equivalence, I will say it also both ways. So for any strategies of the second one, there exists a strategy of the first, so that's very cool. So this is what I call trace refinement. I said that M1 and M2 trace refine each other if I can always match each other's strategy. And then there was this bisimulation and distribution. And the first results that we had last year was saying, well, trace refinement is undecidable. And bisimulation and distribution is decidable. And for the interesting case, for at least for one case, then this gives you some decidability for trace refinement. So what we did here at Simons with Bartek sitting here was to find logical characterizations. So this is a very simple logic that evaluates on distribution of states. So a distribution satisfies a formula. The formula are very simple. You have true, you have conjunctions, you have a modality, model operator, I would say, as usual in this Hennessy linear type logic, and an atomic formula that tells you what is the weight of your distribution. So when you're looking at a distribution, you just make the sum of all the weights, and you're checking if it's bigger than some number p. And the interesting thing is that two distributions are bisimilar if and only if they satisfy the same formula of this logic, which really you should read the other way around. If two distributions are not bisimilar, then you can find a formula that distinguishes them. That's really what you want to say.
Your diamond doesn't have any probability on it?
No, it just says there exists a distribution. So if I read letter A, then there exists a distribution such that from there we satisfy phi. So it's really the non-deterministic part. And the probabilistic version is really here, when you're looking at the weight of one distribution. And now there's sort of crazy fragment, or crazy, like some syntactic fragment, which restricts the use of disconjunction. So you don't want to have conjunctions, and then this fragment, whatever it precisely is, characterizes trace refinement. So now two distributions trace refine each other if and only if they satisfy the same formula of this form, which again you should read as two distributions do not trace refine each other if and only if I can find a formula of this form that distinguish them. And well, this is a sort of surprising thing. You have a logic, a full logic whose distinguishability is a decidable relation, and you have a fragment of it whose distinguishability question is undecidable. So that's the picture of what I wanted to tell you. There was this notion of probabilistic bisimulation on distributions that turned out to be useful in some questions that we were looking at, let's say motivated by verification of stochastic systems. It was very enriching for me because it made me learn all about a lot of different things. And now the question is, what is this good for? The good first thing that I'm happy with is, well, it has at least one good property. It has logical characterization, which, of course, is incomparable to this one, because the logic that I defined here, it talks about distributions. Distribution satisfies a formula. And here, a state satisfies a formula. So it's not even the same framework. They cannot be compared. And this we've seen already that they really don't tell you the same things about a system. So thank you very much.
Yes, Larry?
About the logic at the very end, is it closed under the one that's decidable and nice? Is it closed under negation?
No.
So okay.
I mean, so I mean, what you would like to have, let's say the strongest theorem, is that the weakest logic is enough to distinguish.
Right, but
so for my theorem, I took the weakest possible logic, in which I didn't need negation. Now, what is your question? If you can do the same and add negations, then yes.
no,
But
theorem is the logic already, in a sense, closed under semantic negation.
Okay, so yeah, so the answer is we don't need that, so we don't add it.
It isn't. Yes. The question is it true that the negation of every
Okay, sorry.
is already closed that way?
No.
Yeah, well, no.
Can you blow up the description of the logic? Yeah. So this second logic, I didn't really understand how it differed from the first. Is it the fact that the diamond phi's there cannot contain the sigma formulas?
So what you should is like, the difference is that this is not closed under conjunctions. And how do we achieve this non-closed?
I can put arbitrarily nested things inside the diamond A. I can have diamond A, diamond B, sigma P.
Yeah, but it has to be the same formula. That's the point. So you can say diamond A and diamond B, diamond A phi and diamond A phi, but not diamond A phi and diamond B psi.
So Prakash, you cannot have a conjunction of two diamonds of the same label.
Aha. I see. Okay. That's what makes it easy.
Yeah.
It's a typical Rob van Glavik insanity.
Yes, yes. I see. Thank you. Yeah, Anupam?
What do you mean by the logic being decidable and the fragment being decidable?
Yeah.
Decide a formula, surely I can decide.
Sure. What I mean is the distinguishability relation. So the trace refinement is undecidable. And trace refinement is asking whether there exists. So I give you two distributions, and I'm asking, does there exist a formula that satisfies one but not the other? And this is the undecidable problem.
Is there a formula of this fragment?
Of this fragment, yeah. So of this fragment, you can decide this, and of this one, you cannot. It's not the same as satisfiability.
Yeah.
I mean, because... yeah.
A bit misleading the way you've written it.
Yeah, so yes. What I mean by this
Dramatic,
fragment
but misleading.
that's true.
So the two formalisms are incomparable. One doesn't, you know, if the original, your model and the 25-year-old, they're incomparable in terms.
I mean, so this is an
So they are different, I mean, right?
yeah. So they are incomparable in the sense that out of this definition, you can extend it easily to say that two distributions are bisimilar for this.
Okay.
And then those two notions are orthogonal, meaning that you can find an example where it's true for one and not the other, and vice versa. But they live sort of in different worlds from at the beginning. So this is.
So which is the right one?
The right one.
I don't think there's a right one. I think the right one is whatever you want to do with it. Yeah. And this one, it was for trace refinement. The other one has a lot of different applications. The question is really, what can you do with each?
Okay, let's thank Nathanaël again.